Hello, my name is Noam Perry, and this talk is about expander random walks, a Fourier-Analytic approach. This is based on a joint work with Gil Cohen and Amnon Tashma. Let me start by describing the setting of our problem. So let G be an undirected graph where each of its vertices are labeled by either a 0 or 1. And let's take a random path of length t along the graph and keep track of the labels we've seen. So we pick randomly some starting vertex and then choose one of its neighbors and move to there, and then choose another neighbor and move to there, and so forth for these steps. At the end of this walk, we've collected t bits. So this entire process just defines a distribution over the binary strings of length t. We call this distribution the random walk distribution. Our main question is, which test functions cannot distinguish t-independent samples from those obtained by a random walk? Clearly, the answer to this question depends on the nature of the graph we chose and the exact labeling system that we are using. So if, for example, we've taken G to be the complete graph with self-loops, then those two distributions would have been the same, no matter what the labeling system is. On the other hand, if we're choosing G to be too sparse and we have several different components, then we can use a labeling system which identifies those different components and then easily distinguish between those two distributions. The most natural family of graphs where these questions seem meaningful are expanders. So those are graphs which are highly unstructured, yet are reasonably sparse. Let me go over the notation I'll be using for the rest of this talk. So G will be our graph. It will have n vertices. It will be deregular. And as I'll be using the spectral definition of expanders, I will denote by lambda the second largest eigenvalue of its normalized adjacency matrix. So for any graph, this value will be less or equal to 1. And the better the expander is, this value will be smaller. I will denote by val the labeling system. So this is just a function from n to 0, 1. And I'll denote by mu the expectation of this function, or the ratio of 1 to the entire image file. So we define two distributions on binary strings of length t. The first one is the independent distribution, where we pick each bit independently, where each bit is set to 1 with probability mu. The second distribution is the random walk distribution, which I just described before. So notice that the independent distribution depends only on the value of mu, while the random walk distribution depends both on G and the exact labeling system. We say that f is epsilon fooled by a random walk if the difference between the expectation of f, where it's given a sample from the random walk distribution, minus the expectation of f over the independent model, is less than epsilon. It turned out that this framework is general enough to state several known results. So the first example I'm going to show is the expander hidden property given by Aitai, Komlos, and Semeredi. This theorem says that for any subset B of vertices of size mu n, if we take a random walk on expanders of length t, then the probability that this path will never leave the subset B is bounded above by mu plus lambda to the t. In our notation, we could use the labeling system to identify the subset B. So we'll output 1 if and only if the vertex is a member of B. And we could choose f to be the binary end function. And with those notations, we can say that the expectation of f over the random walk distribution is bounded above by mu plus lambda to the t. This is in comparison to the expectation of f over samples from the independent model, which will be mu to the t. The second example I'm going to give is the Chernoff bound for expander works given by Gilman and Healy. This theorem says that for any subset S of vertices of size half of n, if we take a walk of length t in the graph and we keep a counter which says in how many steps did we land inside S, then the probability that this counter will deviate significantly from half of t is exponentially diminishing. Again, using our notation, we can use the labeling system to identify the subset S, and then choose an F, which sums the labels we've seen and compare their sum to half of t. It will output 1 if we were close enough, and 0 otherwise. So with those notations, the Chernoff bound for expander walk give us an upper bound on the expectation of F in the random walk model, while the regular Chernoff bound give us an upper bound on the expectation of F in the independent model. The last example I'm going to show is the parity sampler by Tashma. So this theorem says that if we take the parity function and we look at on its bias, so the probability it will output 1 minus the probability it will output 0 in the random walk model, so this value will be bounded by the bias of val itself plus 2 lambda in the power of half of t. This is in comparison to its bias in the independent model, which will be just the bias of val to the t. So I'll now go over our results. All of our results are relevant for balance valuations. So we will assume that mu equals half. I will denote by epsilon lambda of f the supremum of the difference in expectation between the two models taken over all lambda expanders and every balance assignment val. I will call this value the error rate of f. So our main result is that every symmetric function is fooled by the random walk distribution. More concretely, the error rate of a function f, of a symmetric function f, is bounded above by lambda times a polylog factor in 1 over lambda. The main claim which is needed to prove this theorem is as follows. So if we take any value m which is close enough to half of t, then the probability that we'll see exactly m1 in the random walk model minus the probability that we'll see exactly m1 in the independent model, this value is bounded by lambda over square root of t. So if you will think about it, the combination of the regular Chernoff bound and the Chernoff bound for expander walks says that it's very unlikely that f will be given an input which will not be a part of this interval. So outside of this interval, the values of f have very little effect on the final expectation. So if we will show that for values inside this interval, f have hard time deciding from which distribution they came, then we can combine them with the Chernoff bounds to get the aforementioned result. Very similarly to this claim, we also prove that the error rate of majority is bounded above by lambda squared over square root of t. Notice that although the two later results decay with t, so the larger t is, the better the bound is, the total bound for all symmetric functions does not depend on t. We also have results regarding other families of functions which are computable in some restricted computational model. And in all of those results, the error rate of f will be a square root of lambda times a term which depends on the complexity of f itself. So for example, we can take f to be a function which is computable by a Boolean circuit of size s and depth d, and get that the error rate of f is bounded above by square root of lambda times log s to the power of 2d minus 2. We also have results about read-once branching programs and decision trees. I will try to give you a short overview of the proof. So the ideas are much easier to express when we are working with plus minus 1 instead of 0 and 1. So from now on, I assume that those are the inputs, and as val is balanced, its expectation is 0. The main step in the proof is to analyze the behavior of a single character in the random walk model. So let S be any subset of the numbers 1 to t, which says which labels to multiply along the path. So let's say there's a character which says to multiply the first value, the fifth value, and the last value. This will be the character which fit to the subset 1, 5, and t. So we want to bound the expectation of any such character in the random walk model. Notice that as val is balanced in the independent model, the expectation of any character, but the trivial one, is 0 anyway. With those bounds at hand, we can use the Fourier representation of any Boolean function to get a bound on the error rate of f itself. So we expand f in the Fourier form, so as a weighted sum of characters, and we just bound each one separately to get a bound on the error rate of f. This idea is a generalization of the parity sampler, which just corresponds to the entire set 1 to t. To get some better results about symmetric functions, we can do a little finer analysis. So instead of bounding the effect of any single character, we analyze the sum of expectations of all the characters sharing the same sparsity. So the sum of expectations of every character of sparsity k will be denoted by beta k. As for symmetric functions, the Fourier coefficient depends only on the sparsity of the subset k. We can get better bounds using the value beta k. I will not get into the exact calculations of the expectation of any character, but I'll try to give you some intuition about what's going on. So let's take two very simple characters of sparsity 2. And the first one will say to multiply the first label and the second label, while the second character will say to multiply the first label and the last label. So again, we are going to randomly choose a path of length t in our expander, and we will, in the first case, multiply the first two vertices labels, and in the second character, we'll multiply the first label and the last label we've seen. As the labels in the first character are labels of adjacent vertices in the graph, we have much more information about the relation. And so we can guess that they will be much more correlated with one another than the first and last label, which are t-1 edges apart in the graph. If you have some experience working with those kind of expanders arguments, you can expect that the expectation in the first character will be lambda, while the expectation of the second character will be lambda to the power of the distance between the labels, so lambda to the power of t-1. This kind of intuition gets a bit more tricky when we take characters which have higher sparsity. So for example, if we take characters with sparsity 4, we can take a look at those three examples. So we can take the character which choose the first two labels and the last two labels, and compare it to a character which choose the first and last labels and two labels in the middle of the walk. and compare it to a character which should its labels evenly spread along the way, it is much less clear what the expectation will be this time. So the main idea of how to make this kind of calculation is to look at S not as a subset of indices of labels to multiply, but to look at it as the differences between the indices we chose. So delta 0 will be just the first index, while delta 1 will be the difference between the first index and second index, and so forth. And I will denote by P the diagonal matrix which represents val. So the II entry of P will be the val of I. And with a bit of abuse of notation, I will use G to denote the normalized adjacency matrix of this graph. So both P and G are n by n matrices. With those notations at hand, we can express the expectation of the character as a matrix multiplication formula. So we'll think of the ones vector on the right as representing the uniform distribution over the vertices of G. And we will think about G as representing what happens to any such distribution when we take a single random step in the graph. So applying G to the power of delta I is just like taking delta I random steps in the graph and look at what happens to this distribution at this point. Now, applying P is the same as looking at what's the label of the current vertex and multiply this label with the value we currently have. The ones vector on the left just sum all those values we've created. So if you think about it carefully, what we are actually doing is for any path of length P in the graph, we calculate the probability that it will be randomly chosen, and we multiply this by the value of the character evaluated on this path labels. And then we sum all of those calculations to get exactly the expectation of the character in the random walk model. Now, using very simple linear algebra arguments, we can bound this expectation. So if we'll define delta S to be the sum of the minimal value of any two consecutive delta I, we can easily show that the error rate of the character S is bounded above by 2 to the S lambda at the power of half of delta S. With very little effort, we can show that this value is smaller than 2 to the sparsity of S times the square root of lambda to the sparsity of S minus 1. Now, we can use this bound to bound the error rate of any function f by plugging it into the Fourier representation of f. So we can show that the error rate of f is bounded by a sum which have the square root of lambda to the power of k times the L1 norm of the kth layer of the Fourier representation of f. Thus, if the L1 norm of the kth layer of the Fourier representation is known to be smaller than some value to the power of k, we can choose an appropriate value of lambda to make this all sum converge. All of our results about non-symmetric function were obtained by using non-results about the L1 norm of the kth layer of functions which are computable in those models. For symmetric functions, we wanted to do a little better. So notice that we have used a bound which bounds the worst character we could have chosen in any specific layer k. But symmetric functions cannot choose to concentrate all the weights just on specific bad characters in every layer. they spread their Fourier weight evenly along a layer. So we can use this property where they have to average out the effect of every character in each layer to get a better bound on symmetric functions.
To conclude the talk, I'll give some directions for future research. The first point regards the polylog factor in the error bound for symmetric functions. Recall that the bound was lambda times the polylog of 1 over lambda, where the polylog factor came from the use of the Chernoff bound to bound the probability of the unlikely events. So we wonder, can we improve this bound or eliminate it completely? As I mentioned before, we have a better bound for the error rate of the majority function. It is better than the general bound for symmetric functions in the sense that it decays with t. So the longer the walk is, the better the bound is. We've wondered whether we can expect such property for more general classes of functions. So maybe to generalize from majority to every threshold function, or even to every symmetric function. All of our results assumed mu to be equal 0. We analyzed only balanced labeling systems, proving similar results in the case that mu does not equal exactly 0, and to understand the relation between the mu and lambda factors in such bounds will be interesting. The last point I want to mention is about our results regarding non-symmetric functions. So recall that all of those results were obtained by using known bounds on the L1 norm of the Fourier coefficients of each layer for functions that are computable in certain classes, together with a worst case bound on the behavior of each single character. We already saw with symmetric functions that we can get much better bounds by taking into account the fact that although there are bad characters, most of them aren't. So the average effect is much better than the worst one. So to get better bounds for those certain complexity classes, we should consider whether functions from those classes can identify and target the bad characters and concentrate all the weight on them. So if we can come up with some dedicated argument to show that in some complexity classes this is not possible, we should get better bounds.
That's it. Thank you very much for listening. I hope you enjoyed this talk.